Let's begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students and this semester and this opportunity we have to meet together, study your creation. Just pray that you'd guide our thoughts today. Help us again, Lord, to glorify you in what we do, Lord. In your name I pray. Amen. Okay, so I should work for you guys. Wave equation example. I think that would be wise. Well, that's what I say before I try to work it. I may retract that statement. So what I'm going to do is I'm going to work number 1 from section 10.6, all right? I probably have this worked out in my posted PDF, but I think it's good exercise for us to work through it. Scratch that. I'm going to work number 3. It's more fun. I'll regret that. All right, but there's more that's going on in number 3, so let's do that one. Here we have partial squared u partial t squared equals to 4 partial squared u partial x squared. That's my wave equation. For 0 less than x less than pi. And we have t is positive. Great. What's our boundary conditions? Our boundary conditions, fixed endpoint, u of 0 comma t equal to u of pi comma t equal to 0. There's my boundary condition. And then my initial conditions, let's see here. I've got u of x comma 0 equal to x squared times pi minus x. All right, and what else we got? Partial u partial t equals to 0. All right. Oh, I'm sorry. Partial u partial t at x comma 0 is equal to 0. All right. And these are both for 0 less than x less than pi. All right, so what we want to do is solve this using our method of separation of variables paired with Fourier series. It'll be a formal solution in the sense that we're not actually crossing our T's and dotting our I's or whatever about the convergence divergence issue. Does this make sense? Is the initial condition consistent with the boundary conditions? What happens if you put x equal to 0 in to the initial condition? Like, we get what? X equal to 0 gives me 0. What happens if I put x equals to pi? 0, right? Are there any other zeros in between? I don't think so. So if I was to graph this, I believe it basically just looks something like, is it positive between or negative between 0 and pi, this function? Positive, right? So it's got to look something like this, give or take. I mean, it's part of the graph of this is a cubic, which opens, it's a negative cubic, so I guess it's something like this. But what's past 0 and pi doesn't concern us, right? So anyway, so what we expect is, and we're like, shaping the string into this shape, and then we're basically letting it go from that, right? It's got 0 initial velocity, so basically we're plucking the string in this particular shape and letting it go. And math is going to tell us what happens after that. Okay, so let's get to work. So the usual technique, we'll let u of xt equal to x of x, t of t. Plug that in. That gives me x t prime prime equals to 4 times x prime prime t. So that gives me that t prime prime over 4t equals to x prime prime over x. We call that minus k. So we face, let's see here, we face t prime prime plus 4kt equal to 0, and x prime prime plus kx equals to 0. By our usual argument, the boundary conditions imply that x of 0 is x of pi has to be 0. See, to say otherwise would be to require that the time solution produces the 0 that's needed in these boundary conditions, right? And we can't do that without making the time solution identically 0. We don't want to do that. So we have to have the initial conditions, the boundary conditions on x flowing from the boundary conditions on our ultimate solution. All right, so as we've discussed, this implies by proposition 8.3.1 that k is equal to, what is it? How's it go? N squared pi squared over L squared, yeah? Which is actually equal to N squared, as L is equal to pi here. And so our x sub n of x is going to be like sine of nx, right? That makes sense. Just checking with intuition, if you take sine of 0, it's 0. Sine of any integer multiple of pi, again, 0. So for any n, these functions, sine nx, that fit the boundary conditions, right? Then, so thus, k, thus we also have t prime prime plus 4 n squared t equals to 0, which implies that t sub n of t is something like a sub n cosine of 2nt plus b sub n sine of 2nt. I'm adding the n index because, of course, this temporal solution depends very much on our choice of characteristic value k on the n squared choice. So in total, we get u sub n of xt equals to something like, a sub n cosine 2nt sine nx plus b sub n sine 2nt sine nx. And that's going to be good for n equals to 1, 2, 3, you name it. Solves, what does it solve? It solves utt equals to 4uxx and the boundary conditions, right? So because these are homogeneous boundary conditions and because this is a linear PDE, and because of the structure here, I can add these sorts of solutions together and still get another solution which solves the partial differential equation and fits the homogeneous boundary conditions. And so if you can do it for one or two, why not do it for infinitely many? If we do it for infinitely many, then we're hopeful we can fit the initial conditions, right? So we're going to form the blank template solution now, as I call it. Form the blank template solution u of xt equals to a sum, n equals 1 to infinity, of a sub n cosine 2nt sine nx plus b sub n sine of 2nt sine nx. Ay, ay, ay. All right, so now what we do? We want to try to select A sub n and B sub n to fit the initial data. Right? We want to fit that initial data. All right. So u, what's u of x0 become? We put time 0. What happens? When we plug in time equal to 0, the b sub n term's gone, right? So we get no data about the b sub n. But the a sub n, it just becomes, some n equals 1 to infinity of a sub n. Cosine of 0 is 1, and then so we have a sub n times the sine of nx, right? But we want that to match what? We want that to match x squared times pi minus x, right? So what do we need to do? We need to figure out the Fourier cosine, listen to me. We need to find the Fourier sine series for that function, x squared times pi minus x, right? So what's that mean? So we can expand this, right, into a sum n equals 1 to infinity of, let's use a different letter. I'll use a, I don't know, I'll use a script a. Let me use something else. How about like s? There, s. Script s. S sub n sine of nx, where this s sub n is, what is it? It's 2 over pi, the integral from 0 to pi, x squared times pi minus x sine of nx dx. This is Fourier sine series. On 0 less than x less than pi. So to select the coefficient, we have to do this integral. S sub n, yeah. If you want, I can make it less weird here. I mean, you can write whatever you want there. I want some letter other than A, because I want to make a conceptual distinction between that and A. Now, the textbook might use an A for the sine series formulas in the section, but I want you to see logically these are two separate things, right? There's the coefficients which come from building the solution from fitting the boundary conditions, right, and then adding them together. And then there's the coefficients which just come from Fourier analysis on the initial position. These are logically separate. Okay, so we integrate, right? How do you do that integral? Yeah.
I just want to ask, where does the 2 over pi come from?
Ah.
Is that the same every time? Like you did the same thing last time.
Well, it depends on what we're doing, actually. But I'll tell you exactly where that's from in the book. Because admittedly, I have not spent a long time to... So let's see here. If you look back at... come on, where'd you go? So when we started talking about Fourier series, we talked about the full Fourier series, right? And in that, there was no 2. In particular, if you look at page 594 from section 10.3, you'll find formulas for coefficients without a 2. That's for the full Fourier series. That's for the series which is going from minus t to t. So for the series that goes from minus t to t, the formulas for the coefficients don't have the 2 in them, although the constant term's got the a sub naught over 2. So Section 10.4 is the Fourier sine and cosine series. And in there, they derive for us Fourier sine series. Equation 7 on page 609, he's got b sub n is 2 over t, integral from 0 to t, f of x, sine of n pi x over t dx. So here we're taking t equals to pi, so the pi's cancel, and 2 over t becomes that 2 over pi I have up front, but it's the definition on 609, page 609. It's derived in section 10.4. Again, the derivation really just amounts to proposing a sine series and then integrating both sides with respect to sine, and using the fact that like integrals of sines times sines are 0 unless the coefficients match. And then the details of how that works out puts a 2 there, because the integration region is from 0 to pi rather than from minus pi to pi. That's where the 2 comes from in some sense. In another sense, I'm being somewhat disingenuous with you. If you look at different books, you can find 2's in different places. There's conventions being made. Okay, the integral's still sitting there looking at us. How do we do it? Let's see here. So this is really 2 over pi, the integral of pi x squared, sine nx, right? Minus x cubed sine nx, right? Dx from 0 to pi. Now, the calculus 2 way to do this would be to integrate by parts, right? And, I mean, if I was to adopt a sort of differential equations perspective, it's not much better. Like, I could look at this as a differential equations problem, right? I'm really trying to solve what? I'm trying to solve dy dx equal to what? And it's tempting to use differential equations since we know how to. I mean, if I was going to use differential equations, this this means that I have the lambda equals to in repeated 4 times, which means that the undetermined coefficients here would have, oh yeah, it's not good. So like undetermined coefficients, if you try to do this problem with undetermined coefficients, you still got like 8 coefficients. So that's not really a very good economy of calculation. Like integration by parts is probably easier. Right. So we can do that integration by parts, or we could phone a friend. What's your preference? Phone a friend? Okay. All right. See what Mr. Wolfram has to say here. I'll just get the antiderivative, though. I'm not going to, we'll still sort through the antiderivative together, like the evaluation. So I'm not going to try to do the, what I'm going to try to do, I'm going to use Wolfram for is just to get the antiderivative of this expression, okay? And then we'll evaluate that. So I need your help here. So we're going to integrate, what is it, pi x squared sine of nx minus, yeah? Yeah. All right, come on. Try not to drop my computer. Come on. Come on. All right, there we go. Great. Shall I take his simplified answer? Ooh, this is a very interesting looking function, by the way. I think I'm going to take the expanded form of the integral. So this is 2 over pi, all right? And we've got 6 sine nx over n to the 4th. A lot of this stuff is hardly worth writing down, but I'm going to write it down. Minus 6x cosine nx over n cubed plus 2 pi cosine nx over n cubed minus 3x squared sine nx over n squared plus 2 pi x sine nx over n squared plus x cubed cosine nx over n minus pi x squared cosine nx over n plus a constant, but we'll put that constant to 0. How about that? We've got to evaluate this guy from 0 to pi. Now, why didn't I need to write down about half of this stuff? Sine of 0 is 0, but what else? Yeah, sine of n pi is also 0. So all the sine terms, they just work out to 0. So, if you, of course, you're like, well, if you're going to use a computer algebra system to do this, why don't you just do the definite integral with a computer algebra system? Fair enough. I mean, I could do that. I'm just trying to illustrate to you guys a little bit of what's going on here. Let's see here. So that's 0. That's 0. Okay, so we're just left with the cosine. And what happens with cosine? Well, cosine of 0 is 1, but cosine of n pi is, as we've talked about before, minus 1 to the n, right? So what do we have here? We've got 2 over pi, excuse me, 2 over pi minus 6 pi times minus 1 to the n over n cubed plus 2 pi minus 1, oh, I could have combined those, couldn't we? Minus 1 to the n, oh well, it's okay. Minus 1 over n cubed plus pi cubed minus 1 to the n over n minus, oh, another pi cubed minus 1 to the n over n. Oh, that's nice. So those last two terms, these two guys, cancel, right, at pi. Yes, they do. That's nice. And then how about the, let's see here. Let me put a different color. What's the terms at 0 minus what? Man, this is a great Calculus 2 question, isn't it? Let's see here. You know what I'm teaching next semester? Calculus 2. That's right. So if somebody asked you this in Calculus 2, you probably would have been like, why would you do that? Well, there's good physical reasons. Let's see here. So 0 gives me that one. That's 0. That's 0. In fact, the only thing relevant from the 0 term in a non-trivial sense is this guy, right? So that's actually pretty, I could put it on the line above. Let me do that. So minus 2 pi over n cubed. Save myself some board space there. Forgive me for going slow here. Let's see here. I think this simplifies a bit, doesn't it? So basically, we've got minus 4 plus 2, which is a net of minus 4. So I've got minus 8 pi. Oh, the pi's cancel. So I get minus 8 to the minus 1. Minus 8 times minus 1 to the n divided by n cubed. Yeah? And then minus, how does that go? The pi's cancel again. So minus 4 over n cubed, I think. Is that n cubed still? Did I get that right? N? Yes, yes. So I suppose we could simplify that a little bit. This is really just minus 1 over n cubed. I guess I could factor out a 4 there. Minus 4 over n cubed times 1 minus 2 times minus 1 to the n, yeah? Actually, that should be plus. So there you go. We just have to take that, right? We just take that coefficient right there. And that is my S sub n, but by comparison, you can see that this should be equal to the S sub n, which we just worked out is minus 4 over n cubed, 1 plus 2 times minus 1 to the n. All right, great. Now how about the other piece, the b sub n's? What happens when we look at partial u? Yowzers. What's partial u? Partial u, partial t. Evaluate at x comma 0. What do we get? When we differentiate with respect to time, the cosine, it becomes sine. And when we evaluate that at 0, it becomes 0. So the only thing that matters is the sine terms. So to differentiate that, we get 2n b sub n cosine of 0, sine of nx. And that's equal to what? Well, thankfully, that was equal to 0, right? So this is equal to 0. That implies that my b sub n is equal to 0 for n equals to 1, 2, and so forth and so on. So what's my final answer? Thus, u of xt equal to the sum n equals 1 to infinity. What we got here? Minus 4. That minus outside is bothering me. If you don't mind, I'm gonna bring it in. Well, fine, I'll just leave it. I just don't like leaving minuses out front like that. But you know what? Fine. It's not wrong. It's just distasteful. 1 plus, I can deal. 1 plus 2 times minus 1 to the n. I could fold it into this thing and flip a sign there. Anyway, so there's my coefficient, a sub n. Then I've got cosine 2nt, sine of nx. And there you go. That is the solution to this wave equation. All right, so I worked the heat equation yesterday, And then at the end of it, I was like, okay, let's work a related but kind of easier problem, right? So let me try to do something similar here. Modify the problem just a little bit, see how it would have been different. So what I'm going to do, same exact problem, all right? But the difference being we have an initial velocity. And I'm going to make the initial velocity something, not too bad. How about this? I'm going to make the initial velocity 3 sine of 5x. Minus the sine of 11x there. I'll probably regret the second term, but there we go. Suppose that that's the initial velocity. So everything would have gone the same, all the same. Same. Right up until what step? This right here, right? Yeah, so instead of having 0, we'd have what? We'd have 3 sine of 5x minus the sine of 11x. So instead of having b sub n always being 0, we'd get b. We'd get that. Let's see here. 3. So put n equals to 3. What do you got? You got 6. We'd have 6b3 would be 3. Oh, I'm sorry, I can't do math. There's a 5 there, isn't it? We should be looking at n equals 5, right? And n equals to 11, right? So 5, what do we get? Let me erase this monstrosity so I have more room. We got to think through it. But this partial u, partial t at x0 has stuff. And then n equals to 5 gives me what? 10? 10b sub 5, right? Sine of 5x. And then there's stuff, and then we get what n equals 11. What's that look like? 22, right? B sub 11, the sine of 11x, and then other stuff, right? Now all of that's equal to, it has to match up to our initial velocity, which we made up a new exciting non-zero initial velocity of, what was it, 3 sine of 5x minus the sine of 11x. So that basically tells me that b sub n is equal to 0 for n not equal to 5 or 11, but b sub 5 is going to be what? So we can equate coefficients, right? The 10b, I'll do the math, 10b5 is equal to 3, and 22b11 should be equal to minus 1. So my b sub 5 is 3/10, and my b sub 11 is minus 1 over 22. Right? So most of our solution's the same, right? When you get to the answer then, the only thing different is I also have to add in a few sort of anomalous b terms, right? So like plus, we got what, 3/10? That's my b5. And what's b5 have? Sine of what? Not 5t, but sine of 2nt, so it's sine of 10t, right? Sine of 5x. minus 1 over 22. And 2 times 11 is 20, so sine of 22t. The sine of 11x. And there you go. For the slightly modified problem, we get those 2 extra terms. Does that make sense? Yes, no, maybe so. Ask you tomorrow. I'm just kidding, it's not in the final. Ask you Saturday. That's when you're... Would it be helpful or hurtful for you, for me to post the PDE project today? Helpful? Because I'm ambivalent, I'm torn on this because I really don't want you to be working much on this today because I think you probably should be trying to get what you can from the final tomorrow, right? So if there's anything left for you to study, if there's anything you don't understand for the final, it'd probably be wise to try to settle that as opposed to working on this. You know. But if you want me to, I will post it today. You want me to? Okay. All right. I'm going to give you guys the rope to hang yourself with. I mean, it's a saying. Don't do that. Don't do that. Unless you have plans for world domination, in which case, you should end the madness before it begins, I suppose. Wait a minute, no. See, now I got to edit this video. Let's see, where was I? Here's a I need to make that go fast. Good grief. Way too. See, I really should just make it, how can you make it not loop? All right, so what we're looking at here is, so at the middle, at the start of it, it's got a complicated temperature distribution.
It's just a blue screen.
Oh, man. Yeah. You'd think I'd learn. So you guys are fine, but if you do that to your wife, it's a more serious issue. All right. Come on. So I guess what we're looking at here is a really kind of silly initial temperature distribution for the heat equation. But you can see what the heat equation does with fixed endpoints. It always kind of, I don't know. I'm not sure how physically reasonable the initial boundary conditions are here. The initial condition is for this one, but it's kind of fun to look at. Here's another one. It's going to hopefully be more interesting. So here is a solution to a wave equation. Whee! So that's, you can imagine fixing the endpoints of the string, and this is the kind of, although I think that we're still looking at time reversed, which is, it's not exactly. Let me make this a little bit more physical. There we go. Make it go from the speed up time. Whee! Oh, a little bit too fast, I'll say here. So that's what, a wave on a string looks like. And I think the neat thing is, right, is that we can actually do the math and find out what the wave on the string is going to look like. And of course, if you want to analyze waves on a string more deeply, you can do things like look for beats and normal modes, and you can do a lot of analysis on the basis of this math, further analysis. But anyway, I think it's fun to actually look at what some of these look like. We could take like that, and we could plot the first few terms in it and see what happened. Don't worry, I do not intend to do that to you on the PDE project. It's something you should be able to do in a day. I will basically be asking you to walk down the path I've walked with you here for a few problems. All right, enough. Silly wave equation example. Yes, leave. Desmos is nice, though, by the way. All right, so I think we'll take a 10-minute break here. I'll try to start again about 11:50. I'll give you back your test. We'll go over the solution to the test, and then I'll tell you how to solve the Laplace's equation. It's